When Lieutenant Colonel Peter Norman Nissen trudged through the muddy work sites near Étaples in early 1916, architectural history was the last thing on his mind. He was watching British soldiers die from exposure while waiting for proper shelter. The Western Front had rendered conventional building useless. Timber was scarce, skilled carpenters were fighting in the trenches, and every structure had to endure shelling. Nissen, a Canadian-born mining engineer serving with the Royal Engineers, had spent months noticing piles of unused corrugated iron sheets abandoned near supply depots because no one knew how to use them. These curved metal panels, originally meant for roofing, accumulated while men froze in canvas tents that collapsed under snow. The brilliance of Nissen's idea lay not in complexity but in brutal simplicity. He bent those corrugated sheets into a half-cylinder, forming a structure that required no internal frame and could stand directly on the ground. In March 1916, he built the first prototype at Étaples using only standard tools and 6 soldiers with no building experience. The structure went up in under 4 hours. When Nissen presented his design to British command, he made one promise that changed everything. Any infantryman could assemble it in 3 days and all materials would fit on a single lorry. The army tested the idea immediately at Richborough Port, where the 172nd Tunneling Company erected 20 huts in April 1916. Each was 16 feet wide, using about 600 square feet of corrugated steel. The curved shape made rain and shrapnel slide off, and the absence of vertical walls removed weak points. By June, Nissen huts had spread through every British sector of the Western Front. The War Office placed its first large order that August, 10,000 units to be built and shipped before winter. What made the Nissen hut revolutionary was not only speed, but the removal of skilled labor. Conventional military construction needed carpenters, masons, and engineers. Nissen's did not. The metal sheets arrived pre-drilled, holes spaced precisely 14 inches apart. The wooden end walls were prefabricated. A foundation was optional. Crews could bolt the huts to wooden sleepers or even packed earth. A sergeant and 5 privates could unload, lay out, and weatherproof one before nightfall. By late 1916, during the Battle of the Somme, teams were assembling Nissen huts under artillery fire to shelter the wounded. The 16-foot width allowed 2 rows of bunks with a central aisle, fitting 30 men comfortably, or 50 in emergencies. The roof, peaking at 15 feet, gave ample standing height. Adjustable end panels provided ventilation, and the steel's air gaps reduced condensation, a constant problem in canvas tents. By the armistice in November 1918, British forces had erected over 100,000 Nissen huts across Europe, the Middle East, and Africa, serving as barracks, hospitals, depots, and command posts wherever quick shelter was needed. The plans Nissen submitted to the War Office in April 1916 explained his hut's success. Traditional buildings relied on frames, posts, beams, and trusses, requiring precision cuts and fittings. Nissen discarded framing altogether. His curved corrugated panels were self-supporting, wall and roof in one. Each 16-foot sheet overlapped the previous by 3 inches, and bolts passed through 3 layers of steel, forming a continuous shell that spread stress evenly. The assembly process was designed to be foolproof. Step 1. Lay wooden base plates in a rectangular outline. Step 2. Bolt upright wooden ribs to the base at 7-foot intervals. Step 3. Fasten the first corrugated sheet to the ribs and anchor it to the base. Step 4. Add the next sheet, overlapping and bolting it to the first until the half-cylinder takes shape. Step 5. Install the prefabricated wooden end walls, complete with doors and window frames. With a trained crew, total assembly took about 72 hours. Inexperienced troops managed it in 4 to 5 days. Throughout the summer of 1916, the British Army tested this process at training camps in Dover and Southampton, timing various units to set accurate deployment standards. What made Nissen's design distinct from later copies was how closely it aligned with available wartime resources. He built around what Britain could actually manufacture under pressure. The corrugated steel sheets were 26 gauge, durable enough to resist damage, yet light enough for 3 men to carry without machinery. The curve's radius was carefully calculated so existing British sheet metal rollers could form it without retooling. Every bolt was 7/16 of an inch in diameter, the same type used in shipbuilding, so no special supplies were needed. Wooden components, base plates, end walls, ribs, were made from whatever timber was on hand, pine, oak, or even reclaimed wood from ruined structures. This adaptability made the design nearly universal. In Mesopotamia in 1917, troops replaced the wooden end walls with bricks taken from destroyed villages. In Egypt, engineers built directly on sand and substituted local palm trunks for milled lumber. The central idea remained unchanged. The curved corrugated shell provided a weatherproof, self-supporting structure no matter what the details were. At Vimy Ridge in March 1917, a Canadian unit assembled a Nissen hut under active bombardment, working in 30-minute intervals between artillery barrages. The shelter was completed in just 18 hours and immediately housed 40 wounded soldiers from the assault. The logistical advantages were extraordinary. A single railway flat car could carry enough material for 8 complete huts, 48 corrugated panels, wooden components, and hardware. At a major military camp in France, construction teams worked in shifts through 1917, completing one hut every 6 hours. By October that year, the camp had expanded to accommodate 100,000 troops, nearly all housed in Nissen structures. Its hospital zone alone contained 300 huts with beds for 12,000 patients. During the German Spring Offensive in March 1918, when 20,000 additional wounded arrived, workers erected 70 more hospital huts in just 11 days. The Nissen's success drew global attention. In September 1940, over a year before Pearl Harbor, the U.S. Navy sent Commander George F. Dorrit of the Bureau of Yards and Docks to Britain to study temporary military structures. After touring RAF bases, Army camps, and naval facilities for 6 weeks, Dorrit's classified November 1940 report devoted 18 pages to the Nissen hut. He recorded build times, materials, and interviews with British officers who had used them since 1916. His verdict was clear. The Nissen hut was the fastest deployable building ever created, but it would need adaptation for U.S. needs. Following Pearl Harbor on December 7, 1941, those adaptations began. The Navy's Civil Engineering Corps selected Quonset Point Naval Air Station in Rhode Island as its test site due to active projects and rail access for prototype shipping. Commander John B. Cyrus led the redesign team, using the specifications Dorrit brought and the original Nissen blueprints provided under Lend-Lease. The first American prototype appeared in February 1942. Outwardly similar to the Nissen, it differed in key engineering principles. Where Nissen's huts relied on the corrugated sheets themselves for structural strength, the Quonset design added an internal steel skeleton, curved arches made from rolled steel channels that supported the weight. The corrugated panels became non-load-bearing cladding, fastened with self-tapping screws instead of bolts. Cyrus argued this approach would yield stronger structures, able to handle heavier loads and better support electrical and plumbing systems. He was right on both counts. The Quonset design was sturdier and better equipped. But it came at the cost of the simplicity Nissen had intentionally preserved. The addition of a framework meant Quonset huts arrived as a greater number of components, demanding more assembly steps. A standard 40-foot Quonset required 14 steel arch ribs, each weighing about 90 pounds, spaced precisely and bolted to the foundation plates. Only after the skeleton was complete could workers attach the corrugated panels. Nissen huts, by contrast, began with the panels themselves and built outward. This difference in philosophy, frame first versus panels first, added 12 to 18 hours of construction time, according to trials at Quonset Point in March 1942. Navy officials accepted this trade-off, favoring long-term durability over quick deployment. American planning assumed bases would be occupied for years rather than weeks. The Quonset also introduced amenities absent from Nissen's design: fiberglass insulation between the steel shell and plywood lining, integrated electrical conduits, solid wooden floors instead of bare earth, larger screened windows, and doors with U.S. standard hardware. Each improvement made sense for comfort and efficiency, but also added weight, parts, and labor. A complete Quonset package weighed roughly 30% more than an equivalent Nissen hut and required more trucks or rail cars to transport. By May 1942, the Navy had standardized 3 Quonset sizes, 20, 40, and 50 feet wide, with production awarded to the George A. Fuller Company and Strand Steel Corporation. The first mass-produced units shipped to naval bases in June 1942. However, the steel framework that defined the Quonset created a dependence on precision-made parts that Nissen huts never had. Each rib arrived as a pre-bent steel channel shaped for a specific hut width. If even one rib was damaged, warped, or misdrilled, the entire frame's geometry could fail. Nissen huts tolerated small errors because their corrugated panels flexed and self-aligned as crews bolted them together. Quonset ribs, on the other hand, required perfect alignment before panels could be attached, forcing crews to spend hours with levels, plumb lines, and templates to ensure every rib stood exactly vertical and evenly spaced. The bolt count alone revealed the added complexity. A 16-foot Nissen hut used about 200 bolts total, mostly to connect panels and anchor them to the base. A 40-foot Quonset demanded over 700 fasteners, 84 for securing 14 ribs to the foundation, another 100 for cross-bracing, and roughly 480 self-tapping screws to attach 30 corrugated panels. Then came the interior fittings: plywood walls, insulation mounts, electrical boxes, and floor joists, each adding more hardware and more chances for field delays when tools failed or parts went missing. American industrial precision, while excellent for mass production, reduced adaptability in combat zones. Quonset parts were built to tight factory tolerances that assumed perfect conditions, an assumption quickly tested in the field. When the 804th Engineer Aviation Battalion arrived at Henderson Field on Guadalcanal in January 1943, they found that humid ocean air had rusted the bolt holes on several ribs during shipment. Because the structure depended on exact geometry, the damaged ribs couldn't be replaced or repaired locally. The engineers waited 3 weeks for replacements from Pearl Harbor while troops slept in tents. Even the insulation system, though improving comfort, slowed assembly. Quonset specifications required fiberglass batting between the corrugated exterior and the interior plywood, forcing a 3-stage process. Build the frame, attach the outer panels, then install insulation and interior walls. Nissen huts, by contrast, were single-stage builds. Once the panels were bolted, the shelter was ready for use, and interior upgrades could follow later if time allowed. At Camp Endicott in Davisville, Rhode Island, where CB battalions trained in 1943, Navy instructors ran direct time trials comparing both systems. An experienced team could assemble a Nissen-style hut in about 48 hours. The same crew needed roughly 96 hours to complete a comparable Quonset hut with full insulation and interior finishing. Electrical integration added yet another layer of complexity that slowed field deployment. Quonset huts came with electrical conduits built directly into the framework, which meant electricians had to work alongside the structural crews instead of arriving afterward. At large naval air stations with ample skilled labor, this simultaneous work process was manageable. But in combat zones with limited personnel, it caused serious delays. Electricians and construction teams often interfered with each other's schedules. The 6th Naval Construction Battalion in the Solomon Islands reported in April 1943 that electrical installations alone delayed the average Quonset completion by 2 full days, since qualified electricians were shared among multiple sites. The floor system proved to be another major bottleneck. Nissen huts originally had no built-in floors. Troops laid wooden duckboards or poured concrete once the structure was finished. Quonset huts, however, required a full flooring system of pressure-treated joists, plywood subfloors, and finished planking installed during construction. This made interiors cleaner and more comfortable, but significantly extended build time. When Major General George Patton's Western Task Force landed near Casablanca on November 8, 1942, his engineers were ordered to build camps for 35,000 troops using Quonset huts shipped from Virginia. Field conditions quickly exposed flaws. Lieutenant Colonel Paul Thompson of the 16th Engineer Battalion reported that the steel framework wouldn't stabilize in Morocco's soft coastal sand. The anchor bolts twisted and the foundation plates sank unevenly. His December 1942 after-action report noted that each hut took about 4 days to complete, most of the delay caused by shimming the frames to prevent collapse. Meanwhile, British forces in North Africa used Nissen huts shipped from Alexandria. The 512th Specialist Team of the Royal Engineers set up a field hospital outside Algiers beginning November 12, 1942. Working with local laborers who barely spoke English, they completed 16 huts in 9 days, without foundations. They laid railway sleepers on leveled sand, bolted the corrugated panels directly to them, and reinforced the base with sand berms. When windstorms struck later that month, several unfinished Quonsets toppled because their frameworks weren't yet clad, while the completed Nissen huts remained intact thanks to their self-supporting shells. In the Pacific Theater, these differences became even clearer. The 1st Marine Division received Quonset huts on Guadalcanal in February 1943 after months of living in mud-soaked tents. Gunnery Sergeant Robert Leakey, in his memoirs, described crews struggling in 100-degree Fahrenheit heat and 80% humidity. The metal frames became too hot to touch by mid-morning. Workers had to pause through the day, stretching 5-day builds into 2-week efforts. In contrast, Australian forces at Port Moresby used simplified Nissen-style huts produced in Sydney. War production records show that these all-metal versions, which omitted wooden end walls, could be completed in about 36 hours. Speed was critical during rapid base construction efforts. When Admiral Chester Nimitz ordered the rapid development of Funafuti Atoll in the Ellis Islands in March 1943, planners needed housing for 5,000 men within 60 days. The 2nd Naval Construction Battalion arrived with both Quonset materials and British Nissen huts supplied through Commonwealth channels. Lieutenant Commander Joseph Blondin divided his crews to test both systems under identical coral atoll conditions. His May 1943 report gave precise results. Nissen huts averaged 54 hours from start to finish, while Quonsets averaged 91 hours. the difference driven mainly by frame alignment and interior finishing. That gap became crucial during emergencies. After the Battle of Midway in June 1942, the U.S. Navy needed immediate hospital expansion at Pearl Harbor for incoming wounded. Using Quonset huts with their heavy foundations, internal frames, and insulated interiors would have meant at least a 2-week build time, far too long for wartime conditions. Instead, the crews adopted a hybrid method. Nissen-style corrugated shells were erected in just 3 days, with medical interiors installed afterward. These emergency wards stayed operational through 1944, treating over 2,000 patients during their service. However, differences in weather resistance soon revealed new trade-offs. The Quonset's insulation made interiors more livable in both heat and cold, but its layered wall design trapped moisture. In the perpetually damp Aleutian Islands during 1943, this led to condensation buildup between the steel exterior and plywood interior, causing rust and mold. By contrast, the simpler single-layer Nissen huts with natural airflow through their corrugated seams remained drier, less comfortable perhaps, but more resilient to the elements. American industrial power turned the Quonset into a mass production success on a scale the handcrafted Nissen could never achieve. By July 1943, Strand Steel Corporation's plant in Richmond, Indiana was producing 200 complete Quonset packages per day, while George A. Fuller Company's Pennsylvania facility added another 150 daily. That meant over 100,000 huts per year, an output that required an unprecedented degree of standardization. Every component had to be interchangeable. A steel rib made in early 1943 had to fit perfectly, with panels manufactured more than a year later. This precision was achieved through die forming and jig-based fabrication, techniques far beyond the decentralized, small-scale British system that had produced Nissen huts. Standardization extended beyond materials to design philosophy. Quonset huts were built in only 3 widths, 20, 40, and 50 feet, with lengths in 10-foot increments. This modularity let logistics officers plan shipments with mathematical precision. A single 40-foot flat car could carry one full 40 by 20 package. Transport ships allocated cargo space in Quonset unit equivalents, and supply depots stocked universal replacement parts. Any 20-foot rib fit in any 20-foot hut, anywhere, at any time. This eliminated the flexibility and improvisation that defined Nissen construction, but made it far more uniform and predictable. Financially, the contrast was striking. In 1943, a 40 by 20 Quonset hut cost the U.S. Navy about $850, including materials, insulation, electrical wiring, and flooring. A comparable Nissen hut, based on 1918 British records adjusted for inflation, cost about $230. The Quonset's superior comfort and systems justified the higher price in American doctrine, but the 300% cost increase multiplied rapidly across thousands of units. By the end of the war, total U.S. spending on Quonset production exceeded $140 million. Production numbers told 2 different stories of success. Between 1941 and 1946, the U.S. manufactured about 170,000 Quonset huts, roughly 34,000 per year. Britain, with far smaller industry, had built around 100,000 Nissen huts during just 3 years of World War I, averaging 50,000 per year. The difference lay not in capacity, but in design complexity. Nissen huts required only corrugated steel, basic fasteners, and rough timber, components any sheet metal workshop could make. Quonsets demanded precision-formed ribs, pre-drilled panels, insulation, electrical fittings, and lumber coordination, linking multiple industries in one supply chain. The engineering trade-offs showed most clearly in adaptability. Quonset huts could be upgraded after construction. Partitions, heaters, wiring, and heavy equipment could be added to the internal steel frame. This made them ideal for semi-permanent bases and rear area facilities. At Naval Air Station Alameda in California, more than 400 Quonset huts were installed in 1943 to serve as workshops, classrooms, and offices. Many remained in use until the base closed in 1997, over 50 years later, proving the long-term value of the American approach. Yet that same framework was a liability in the field. When the 43rd Infantry Division moved from Guadalcanal to New Georgia in June 1943, their Quonset huts could not be dismantled for relocation. Once bolted together, the heavy steel ribs were difficult to unfasten without damaging the threads, and the panels were useless without the framework. The division abandoned 42 complete huts. Nissen huts, however, disassembled almost as easily as they were built. The bolted panels separated cleanly and could be reused anywhere. British forces routinely relocated entire Nissen camps, moving the same structures from Egypt to Italy to Greece as the front advanced. The real divide between the Nissen and Quonset legacies emerged not during the war, but in the decade that followed. When World War II ended in August 1945, the US military was left with roughly 70,000 surplus Quonset huts scattered across bases being decommissioned. The War Assets Administration, responsible for liquidating excess equipment, began selling the huts in 1946 for $200 to $600, depending on size and condition. That same year, over 15,000 Quonsets were purchased by farmers, small business owners, and families struggling with post-war housing shortages. Thanks to their insulation, integrated floors, and built-in wiring, the huts could be occupied immediately, as homes, workshops, or storage buildings. This sparked a uniquely American architectural phenomenon that lasted for decades. Even today, one can drive through rural Iowa, Kansas, or Nebraska and see Quonset huts repurposed as grain silos, tool sheds, and machine shops. Small airports across the Midwest used them as hangars well into the 1970s. The University of Illinois even built a Quonset village in 1946 to house returning veterans. 260 huts that were meant to be temporary, but lasted until 1972. Ironically, the very traits that had slowed their wartime deployment, insulation, flooring, structural rigidity, made them ideal for civilian life. They were durable, comfortable year-round, and easy to modify. The steel framework could hold shelving, cranes, or even drywall for those wanting a more conventional look. Across the Atlantic, Britain took the opposite path with its Nissen huts. After 1945, they became symbols of wartime deprivation. The military sought to erase them. Thousands were dismantled, their corrugated panels sold for scrap during the post-war steel shortage. Some survived on Yorkshire and Scottish farms as barns and tool sheds, but the government discouraged widespread reuse, preferring to distance national identity from the visual memory of austerity. By the mid-1950s, most Nissen huts had disappeared from the British landscape, except in remote rural areas where practicality still trumped aesthetics. Architectural elites on both sides of the Atlantic rejected the designs. In the US, architectural journals of the 1950s dismissed Quonset huts as metal blights, and Frank Lloyd Wright derided them as pig shelters unfit for human habitation. In Britain, the Royal Institute of British Architects went further. A 1948 publication described Nissen huts as corrugated embarrassments to be removed as soon as economically feasible. These criticisms ignored a simple truth. Both designs had provided shelter, warmth, and function for millions when no other options existed. Commonwealth nations carried forward Nissen's principles. Australia's post-war reconstruction used simplified curved roof huts inspired by his design, but stripped of American framework complexity. They became quick, low-cost housing for immigrants and workers in remote outposts through the 1960s. Canada's Department of National Defence continued to manufacture Nissen-style huts for Arctic and subarctic bases, where Quonset insulation systems failed. The single-layer steel shells prevented ice buildup that crippled the heavier American models under snow load. By the Vietnam War, both designs had been surpassed. The US military introduced modular, containerized housing that could be airlifted by helicopter and assembled in hours. These systems used lightweight aluminum frames and composite fabrics. Far faster and easier to deploy, but exponentially more expensive. A single modern shelter unit costs about $50,000, compared to $850 for a Quonset hut in 1943. Adjusted for inflation, today's shelters are roughly 6 times more expensive per square foot, yet serve the same essential purpose. The enduring lesson of the Nissen versus Quonset's story is that military engineering often mistakes improvement for necessity. Peter Nissen designed his hut by asking a single pragmatic question. What's the absolute minimum needed to keep soldiers dry and alive? His answer, curved corrugated metal bolted together, defied every building norm. No foundation, no framing, no skilled labor, just speed, simplicity, and survival. A sergeant with 5 exhausted soldiers could build one in 3 days, even under artillery fire. The American engineers who reimagined it asked a different question. How can we make it more comfortable and permanent? Their solution was more sophisticated architecture, but less effective as emergency shelter. That contrast between the optimal and the adequate runs through all of military history. The balance between what is ideal and what is simply enough to endure. The M1 Garand rifle outperformed the bolt-action Springfield in nearly every respect, yet it was heavier, more intricate, and demanded greater maintenance. Sherman tanks proved dependable and easy to repair, but their armor was inferior to that of German Panthers. In the end, American forces triumphed not through flawless equipment, but through adequate equipment fielded in overwhelming numbers. The Quonset hut fit perfectly into this pattern. It was a better shelter than the Nissen hut, more durable, more comfortable, but armies needed speed more than they needed perfection. When the 1st Marine Division was slogging through Guadalcanal's mud in late 1942, a weatherproof hut built in 3 days would have been far more valuable than an insulated, electrified one completed in 10. Modern military planning has largely forgotten that calculation between speed and quality, a balance that World War II commanders confronted daily. Today's U.S. construction standards assume that infrastructure will be in place before deployment, that supply chains will stay open, and that work can proceed without enemy disruption. Those assumptions held true in Iraq and Afghanistan, where American forces controlled the skies and had months to establish forward bases. But they would collapse in a peer conflict, one with shifting fronts and contested logistics resembling World War II far more than modern counterinsurgency wars. The Marine Corps acknowledged this gap in 2019 when it revived Expeditionary Advanced Base Operations, EABO, a doctrine that essentially rediscovers Nissen's lesson. Rapid, flexible construction matters more than comfort. That divide between speed and sophistication extends well beyond the military. Modern civilian construction, too, prizes complexity. Building codes demand wiring, insulation, foundations, plumbing, and a web of specifications that make structures safer and more comfortable, but also slower and vastly more expensive to build. For permanent housing, this makes sense. For emergencies, it doesn't. After Hurricane Katrina in 2005, the Federal Emergency Management Agency, struggled to provide immediate housing. Its manufactured homes required concrete pads, utility hookups, and weeks of setup per unit. A simple Nissen-style structure, lightweight corrugated steel bolted into an arch, could have gone up in days using only local materials, providing instant relief while permanent rebuilding followed. In total, America produced 170,000 Quonset huts, an extraordinary industrial feat that housed millions of service members around the globe. They succeeded as semi-permanent base structures, but they couldn't match what 6 British soldiers had achieved in 1916. A weatherproof hut assembled in 3 days with nothing but hand tools and grit. That was the true innovation: speed, simplicity, and self-sufficiency. The Quonset improved every feature of the Nissen except the one that mattered most in combat: getting soldiers out of the mud before the next bombardment began. Today, the curved corrugated huts that still stand across farms and decommissioned bases symbolize 2 opposing philosophies. The surviving Quonsets prove that American engineering made them strong enough to outlast their era. The vanished Nissens prove that British engineering made them simple enough to be built anywhere, anytime. Then abandoned, without a second thought when the war moved on. Both were triumphs in their own right, but only one could rise while the shells were still falling. That is the line dividing architectural success from battlefield necessity.